Hello and welcome to this module 5. In this module, we will be seeing about detailed design of counters. So in this module, we will also be seeing about how to optimize your counter design, and we will also see how you can implement counters using the various flip-flops like the D, SR, JK, and the T flip-flops. So we will have some initial examples on T and D flip-flops, and then some examples on SR and JK flip-flops. So let's say our design here is to design a 3-bit binary counter using T flip-flops. So as you can see, the binary counter has a binary count sequence of 0, 0, 0, and then it goes to 0, 0, 1, then 0, 1, 0, 0, 1, 1, and so on until it reaches 1, 1, 1, and then goes back to 0, 0, 0, and then keeps on continuing until you have a clock pulse. So remember that in a counter, we do not have any inputs generally, and also the count sequence is simply triggered by the positive edge or the falling edge of the clock. So we also assume here that the flip-flops have a minimal delay, so that the flip-flop state changes within a short time of a rising or a falling edge. And the output itself is basically the states of the flip-flop. So let's say if a flip-flop you have here is 3 flip-flops, and it's named as C, B, and A. And if the flip-flop states are 0, 1, and 1, then the state of the counter or the counter value is simply given as 0, 1, 1. So we basically assume that we are going to have C as the most significant bit and A as your least significant bit. And then as you can also see that whenever the counter goes to a value of 1, 1, 1, it's going to go back to its initial state of 0, 0, 0. And it also is assumed that initially the counter always starts at initial value of 0, 0, 0. So what is that we need to design? So we need to design a 3-bit binary counter. So how do we go about designing that, and what do we need? So since we have a 3-bit binary counter, so we are going to have 3 bits of the state, and therefore you need 3 flip-flops. So that's the first thing that you would need to determine, that how many flip-flops you need for a design. So if you are having an n-bit binary counter, then you would actually have n flip-flops. The second one that we need is what type of the flip-flop equation or table that you need. So whenever I have the current state, and if you want to calculate what is the next state, which is in this case for the flip-flop C, so you have a current state which is C, and the next state is C++. So then we basically try to use our next state equation. So our next state equation starts as something like, say T of with the input. So we have T of C, and therefore it says C plus is equal to C of E XOR C. So that's for the T flip-flop. Similarly, for various flip-flop, you have your next state equations, and that's what we actually use in analysis. But in the case of a design, we actually would need to consider our excitation equation, so, or the excitation table. So we have already seen in our earlier modules, like we can also represent our flip-flops by excitation table, as here for the T flip-flop, or the excitation equation. So basically what the excitation equation tells us is, if I have a current state which is C, and my next state is C++, what should have been my input to trigger from C to C++. So using this, we can then create a table for TC and then try to determine this circuit. So that's basically what the next one is. Our ultimate goal is to actually determine what these functions are going to be that are actually feeding as an input to our T flip-flops. So that's what the design is. So in analysis, you were actually given this and you were actually trying to find out what this transition is. That is, what is the equations for C++, C+, B+, and A+. So in this case, you are given C and C+, B and B+, and A and A+, and you are expected to actually come up with what would your values of TC, TB, and TA would be, and thereby then figure out what are these circuits in order for them to happen. Okay, so to summarize it, this step is going to be, or these steps are going to be similar for either designing of a counter or even designing of a general FSM. But designing of a counter is a little bit straightforward compared to the designing of an FSM, because in FSM you would actually have both Moore and Mealy's representation and different types of derivations for it. So therefore we start with the design of the counter and then proceed to the design of an FSM. So start with step 1, we need to derive the state transition diagram. So this is not generally needed, but if you're trying to derive something from scratch, then it is a good idea to actually derive the state diagram. The next, what we do is we create a table with your current state and your next state. So you have, as you see, we have a 3-bit counter, so therefore we will need 3 flip-flops, and each of these flip-flops will have state variables. So you have 3 state variables that represents this, and as you can see, there is no input as in this case, and so we basically will need to create this table. So for example, we have here is our initial value 0, 0, 0, and then our next value will be 0, 0, 1, and then similarly we have 0, 0, 1 as a current state, and our next state will be 0, 1, 0, and so on. You can construct the table. Once you construct the table, so then what we do is we can use either the excitation table or the excitation equation and try to determine what your input is. So as we know that in your excitation table or excitation equation, it considers what your current and your next state is going to be, and then tries to determine what the input that caused that transition. So here, as you can see, this is our next state equation. So therefore we can say 0 XOR of 0 will pretty much give you 0. And similarly, 0 XOR of 0 again gives you 0. And then 0 XOR of 1 will give you 1. So therefore this basically is what we actually try to determine. So now similarly we try to calculate for all of these combinations. So here again, as you can see, we will have 0, 1, 1, and now we actually have this table, and now treating this as your outputs for your K-map, we are going to derive equations for TC, TB, and TA, and once you derive the equations, then we can actually try to, that would be your step number 4, where you derive the equations for the inputs of the flip-flop, which are here, and then we will need to construct this entire diagram, which is step number 5, and that basically will complete your design of a counter. So here is the actual example that was shown on the previous slide, which has been solved. We have actually indicated the steps here. So here you can see we create, so we start with a 3-bit counter, so we need 3 flip-flops. So we assume that we need 3 states. So we name those state variables as C, B, and A. So then we basically create this table, which is having present state and the next state. So that's based off the different, say you had 0, 0, 0 as a state S1, and then you went to a different state, which is 0, 0, 1, which is say S1, sorry. And then you went to another state 0, 1, 0, which is state number 2. So that's how from here we got to this present state and the next state table. So once you have this table, then we use this excitation table or excitation equation. So here you can see that C plus, you look it up. So in this case, this is basically Q, generic Q and Q plus. And then we can see for 0, 0, T should have been 0. So that's what it is. Or you can simply apply the equation here, which is 0 XOR 0 will give you 0, and you create this table. So once we create this table, so using, we are basically going to solve for the equations for these 3. So therefore, you can see here, TA, you have nothing but 1s. So therefore, it's straightforward. TA is nothing but 1. So now for TC, you can see that we are solving that using a K-map, and we see that the equation is AB. And similarly for TB, our equation is simply A. So therefore, when we actually construct it, so TC, so here you can see this is A dot B. Here, this was simply A. So we actually connect it. So in some cases, you really don't need to connect this. You can simply specify this as A, B, and not worry about these feedback connections, because they are just basically will be, represented by their, pins or variables. And then obviously TA is nothing but 1. So that basically completes the binary counter, 3-bit binary counter design using T flip-flops. And we have actually seen the analysis of this, which is you were given this and you went all the way in deriving these equations and then applying next state expressions to calculate C plus, B plus, and A plus, and then you created a table which is pretty much this table, and then from here we actually implement or did an implementation of the state transition graph or the state diagram. All right, so here is another example. So it's the same example. What we are going to do now is we want to implement that using a D flip-flop. So as you can see, the procedure is the same. So again, this is a 3-bit binary counter. So here is our count sequence that is flowing. So once it goes to 1, 1, 1, it's going to go to 0, 0, 0. And so now this is going to be our next state, which is same. So now when we look at our D flip-flop, our excitation equation is pretty much D is equal to Q plus. So technically, you don't have to create something like DC, DB, and D of A, because they're going to be identical to C plus, B plus, and A plus. Therefore, it's simply what you can do is simply replace those by simply DC, DB, and DA. So there is really no need whenever you try to do a D flip-flop implementation to actually have an additional 3 columns. So now what we do is, as you can see, we need to find the equations for this. So we have a K-map for each one of them. So this, since you have just 3 variables, you can choose which variable is in your row, which variable is in your column, etc. You can choose to have them in a different order, etc. So, and then over here you can see we calculate the values of or the expressions for dA, which is given here, and then we calculate the expressions for dB, that is shown here, and then we calculate the expression for dC, that is shown here. So once you have these expressions, so now we will like to implement it. So here you can see there's a bunch of XORs, so therefore we are using a bunch of XORs to do it. The other way to do it is also, since we already saw the implementation for a T flip-flop, so here it tells you how a T flip-flop can be derived from a D flip-flop. So it takes an input value, say let's say it's A, and you basically you can see here, let's say this is like, so example, a B D flip-flop. So you will have say B plus here. So technically you XOR that with that. So therefore this will simply be A XOR B. So you can also just use the XOR function to create it. So that's what is happening here. So here you can see that in our initial implementation, we saw that we had a function here is AB, then we had a function here is A, and then we had a function that is 1. So now all you need to do is just do an XOR with the input or the state variable of that flip-flop. So therefore you do an XOR with that. Then similarly you do an XOR with that, and similarly you do an XOR with that. So this will be another easy way to convert an implementation that you have already calculated with T flip-flop into a D flip-flop. Or you can also do the long way that is shown here, so where you have the functions that are shown here. So this function here is nothing but will give you A dash.